Just as we had to exercise some caution at the end of chapter 2, because graphs can be misleading, sometimes on purpose, sometimes not, we also have to have a little caution when we look at associations. So let's look particularly at what I'm talking about. So extrapolation, it's when you use the regression line, but instead of going between the min and the max values of the x and predicting y's, you go beyond that min or max value and you get outside of that range to where it looks more like a straight line. Because once you get outside that range, you can't really tell. So for instance here, if we look at this, it appears to be, you could put a line pretty much at a 45-degree angle. But if you notice, if you got beyond this material to the right-hand side, these blue dots, it might now start curving in some other direction. That would be extrapolation. So we also have what are called regression outliers, which may affect it. And if you look, they have an arrow pointing to one, and that will affect a correlation quite a bit. So a regression outlier, it's far away from the trend that we're looking at. It's influential if the x value is relatively low or high compared to the rest of the data. Influential observations tend to pull the regression line toward that data point and away from the rest of the data. So if we simply went by numbers, instead of a line at a 45-degree angle, it would be leaning further down there toward the regression outlier, and that would really throw off our calculations for our estimates for the y values along that line. Here's the scatter plot, and we're going to be making scatter plots both in StatCrunch and on our TI calculators or whatever graphing calculator you have. You notice you could put a straight line that's pretty horizontal along the bottom in between 5 and 6, and it would seem to work for most of the data. The two at the top, the two outliers, would influence it quite a bit. So again, correlation doesn't imply causation, it's association. So as one thing goes up, something else also goes up. That doesn't mean that one causes the other. It means when one goes up, you probably can look for the other one to go up, but you don't know how much or if it actually causes it, or, maybe something's causing them both to go up. So a lurking variable is a variable that's not accounted for. So suppose you have ice cream sales going up and drowning going up. Does one cause the other? No, there's a lurking variable here. It's temperature. When the temperature goes up, more ice cream sold and people go swimming more often, and that results in more drownings. How about the reading level and shoe size? If someone's reading level increases, does their shoe size increase? Or when their shoes become bigger to fit their feet as they grow, does that increase the reading level? No, these are both caused by age. As people get older, they become better readers, and their foot size changes, until they become adults at least. How about the childhood obesity rate and the gross domestic product? That's what the GDP stands for. So both of these actually have a lurking variable of time. Over time, the gross domestic product, the amount of products produced in the United States increases. And over time, obesity is increased also in the U.S. So there's something called Simpson's paradox. It says when the direction of association between two variables changes after we include a third variable and analyze it. So it's in one direction, and then we add a third variable, and the direction changes. So here's an example. So if you look at this chart, it certainly looks like smokers have a less of a chance of dying than non-smokers, which seems a little odd based on what we currently know. Now, what if we break it down by age? You notice in the far left, people 18 to 35, most of them are still alive who are smokers, right? Because it hasn't had time to affect them yet. But as you keep coming from left to right with age, you notice the numbers change. So 5 compared to 174, 174 is really quite a bit bigger. It's like, about 35 times as big. The next column, 41 compared to 198, that's maybe 5 times as big. 55 to 64, they're getting close to a 1-to-1 ratio. And then 65 plus, And it looks like there's about 6 times people dead than there are alive. So that's what that explains it with, that what's happening here is the effect of the smoking isn't evidenced until people become older. And if you did this in terms of bar charts, you can see this. Okay? So a lurking variable may be a common cause, something that explains both of them. As like when the temperature rises, more people go swimming, so there are more drownings, and more people buy ice cream. In practice, there's not a single variable that explains a response variable quite often. There's several causes that, say that affect whether you have diabetes. It might be genetic in part. It also might be your diet. So when you have two explanatory variables that are associated with the response variable, but also associated with each other, they're said to be confounding. So the lurking variables are not actually measured in the study. They've been missed. And they confound us when we're trying to figure out what's going on.